Hi guys, back during our physics unit we learned a lot about forces, and forces probably apply to some of the projects that people are working on, so this might be a good review for you if you're dealing with something where there are a lot of different pushes and pulls that have to work together in order for something to work. This is a picture of a free body diagram. It shows you on the left-hand side the real-world situation where there's this person rappelling down a mountainside. And then it's a simplified version of that over here. And then finally you get to the free body diagram where all you have are arrows coming off from the dot, which is supposed to be the person. And those arrows represent the different forces acting on that person. And how they labeled these forces is a little bit tricky. You might not necessarily label them this way. The green arrow at the top is the force of friction between the cliff and the man. The brown arrow there in the middle is the force of tension between the rope and the man. And the little gray arrow going to the left is the force of the normal force of the cliff and the man pushing against each other. And then there's the force of gravity between the earth and the man. Notice that these forces are all what we call action-reaction pairs. This is Newton's third law of motion, which says for every action there's an equal and opposite reaction. So that means any push or pull has a push or pull in the opposite direction. Notice that action-reaction pairs happen with two different objects. So go back to the first one at the top. The friction is between the cliff and the man. The man has friction against the cliff has friction against the man. There's tension in the rope. The tension is between the man and the rope. So the rope pulls on the man pulls on the rope. Same thing with the normal force. The man pushes on the cliff pushes back, and whether you accept this or not, gravity is also a two-way force. The earth doesn't just pull on the guy pulls on the earth. It's just that he doesn't pull nearly as much, so he's kind of losing. But in the end, gravity is an attractive force between two objects. So all forces come in pairs. What's confusing is people have a tendency to pick the wrong pairs. You have to be very careful when you're trying to figure out what the reaction force is to an action force. Just make sure you think about it as it has to go in the opposite direction of the original force, and it has to be on a different object. It can't be the same object. And as long as you remember those two things, usually you can figure it out. Let me give you an example. Okay, here's a tricky example. I've got blue and red arrows on either side of my stick figure dude. He's standing on the earth. Here's the question. What are the action-reaction pairs that I'm showing here? And on the blue side, I'll give you a hint. In the downward direction, oops, I should do that in blue. In the downward direction, as I was saying, I have the force of gravity. What's the reaction force on the man? If this is the force of gravity pulling down, what's the reaction force pulling up? Don't get fooled. It's also the force of gravity, but this time it's the gravity the man exerts on the earth. So this is the force of gravity on the guy, and this is the force of the gravity on the earth. You might have been thinking, though, that the ground was pushing back up on the man. That's what everybody wants to do for this force. Everybody wants to call that the normal force, but actually the normal force is over here. The ground pushes against the man, and the man pushes against the ground. Those are both the normal force, but the ground and the man are pushing against each other. Same thing with gravity. What's confusing is everybody wants to do this. They want to do, the up force is the normal force and the down force is the force of gravity. That's not an action-reaction pair, because the two forces, even though they act on different objects, they're not the same force. They're not a pair. The normal force is not caused by gravity, and gravity is not caused by the normal force. So you have to have the same force acting in both directions on different objects in order to have an action-reaction pair. Action-reaction is Newton's third law. Let's talk about the others. Newton's second law is easy to understand. It's an equation, which might scare you at first, F equals ma, but it's a really simple equation. The force on an object is equal to its mass times its acceleration. All this means is it takes more force to move heavy stuff than light stuff. So you can see we have the force being equal to 10 newtons in order to move the box with the books. When there are no books in the box, we only need 5 newtons of force to accelerate it the same amount. This law can be used to calculate the force on something, or the acceleration, or to find the mass of something, as long as you have the other two variables. Newton's first law happens most often to us when we're in a car with our seatbelt on, or sometimes without. What the first law of inertia says is that an object in motion stays in motion until something stops it, and vice versa. An object at rest stays at rest until something makes it move. So in this case, the car is moving forward at 60 miles per hour. We hit the brake, the car stops because a force acted on the car, but this guy keeps going forward until his seatbelt exerts a force on him to stop him. So objects in motion stay in motion until a force stops them. Or an object in motion that's not in motion, that's standing still, won't start until some force acts on it. You can use inertia to think of mass. The more massive something is, the more inertia it has. It's harder to stop a heavy thing that's moving than it is to stop a light thing that's moving because it has more inertia. It has a tendency to keep doing whatever it was doing before. So if I was going to try and hit two balls, one that's really heavy and one we'll say is really light, the heavy ball has more mass and therefore more inertia. So it's going to take more to change its motion. It'll also be harder to stop that ball once I get it starting than it is to stop the lighter ball. So friction will have more of an effect on my light ball because all forces affect something with less inertia more. And that goes back to force equals mass times acceleration, Newton's second law. A good thing to remember about the 3 laws of motion is that they're all interrelated and interconnected. If one law is applying, the other 2 are as well. So you want to ask yourself, as you're thinking about your project, where do you see forces? Can you draw a free body diagram to show the forces acting on your device? Can you explain how Newton's 3 laws are affecting your device? And that should be good enough for you to explain the physics behind your device if it really applies. And you should check in with me to make sure you're not barking up the wrong tree. Some devices are better suited to other things besides a physics review. See you guys in class.